CSA department at this time, and we are celebrating the golden jubilee of the department during this current academic year. The department itself was established in 1969, and so it's completing 50 years now. So as part of the golden jubilee celebrations, we have organized, thought of a series of lectures under the CSA Golden Jubilee Frontier Lecture Series, and so we have we are planning to get several distinguished people to talk about their works on cutting edge research and so on. So the first lecture actually happened on August the 8th, and the second lecture we are fortunate to have Professor Prasad Tetali from Georgia Tech, and he is actually the first of the Satish Dhawan visiting chair professors to have come to CSA. Okay, so he is the first in that. We are fortunate to have him here. So to introduce the speaker formally, I would like to request Professor Ravi Kannan, who is the first adjunct faculty member of CSA and is a principal research scientist at Microsoft Research.
Hi. It's a great pleasure to introduce my good friend Prasad Tetali to this lecture, and he's actually he doesn't need an introduction, both because of his research, but also because he's an alumnus, so he belongs here. Prasad is now in Georgia Tech. He's a fellow of ACM and SIAM and has many honors and results to his credit. He's also a very, very nice person. So welcome, Prasad.
Thank you very much. Can you hear me okay in the back? So first and foremost, let me thank the Institute and in particular School of Automation, as it was called 35 years ago when I landed here, probably around this time, sometime in August, for my master's by thesis. And earlier, about a month or so earlier, I interviewed first in ECE, because my undergraduate was in ECE, and I bombed that interview pretty badly. And then the next day, it was in School of Automation, and I don't think I did particularly well there either, but somehow the faculty then, some of whom are very much here in the room, took a chance on me, and I'm extremely grateful for that, because otherwise I think I would have wasted a year trying to figure out what I had to do. And indeed those beginnings really laid the foundation of what it means to do research in combinatorics, computing, probability, and algorithms. So those are some of the topics that I've been interested in since starting my master's here. Also, thank you, Ravi, for the introduction. Let me warn you that nothing I say is going to be, particularly frontier research, nothing that was proved yesterday or last year. It's a few years old, not 50 years old, but a little more recent than that. I think for some of the frontier stuff in Markov chains or randomization, you need to, as you've done in the past, you need to get people like Ravi up on the stage to talk to us about. But I hope I will talk about a few things that might be interesting, at least to the beginners and the students in the room. One of the first very exciting results and talks I had heard as a graduate student at Courant Institute, NYU, about random walks was actually a super seminal result that goes back to Ravi Kannan, Martin Dyer, and Alan Fries, about estimating the volume of a convex body in n dimensions using an oracle that tells you whether it's inside or outside the body and so on, and using random walks to sample and using the samples to approximately estimate the volume. So what I'll be talking about are somehow much more lower level in some ways, but there's still lots of open questions we don't know how to answer. Okay, so I spent more time making up the title than the abstract and other things. Once I was told this is sort of in a general audience or institute-wide lecture. So I will apologize up front if some of the slides have basic material, and I'll probably poll in a few minutes to see if there's anybody from the life sciences or other fields outside of computer science and mathematics and engineering, just to make sure. Otherwise, for sure, I'll be insulting some of you at various parts in the talk because of the elementary nature of what I'll say. Okay, so the focus of the lecture is largely going to be on Markov chains, and I picked about sort of 3 stories. The title captured 2 of them by way of chromosomes and some rearrangements, and then although it doesn't say in the title, on this slide, chasing kangaroos has to do with a particular algorithm to solve the so-called discrete logarithm problem. I'll say what it is later. So because I contributed to some work on those 2 topics, but the first story, and my favorite story, because it's not based on anything I've done, but again, one of the stalwarts of the field, Percy Diaconis, is a story about breaking ciphers using Markov chains. So I'll start with that and gradually move on to the other topics. Again, apologies to those, I'm sure people in probability and related fields who might have heard Percy or seen the work that I'll talk about in item 1. So bear with me, but if you haven't seen that, it's a very nice example of an application of finite Markov chains. Okay. So, and again, please, if I lose you at some point or some of the slides don't make sense, please raise your hand. I'll be happy to try and clarify. I might use the board at some point, so I will see if there's some chalk later I might want. Okay, so let's get started. Breaking substitution ciphers in particular, and I tried to somehow put in some Kannada with the help of Google. So here is story 1, right? So breaking ciphers. So the story goes that Stanford has this open door or drop-in consulting service, Stanford Statistics Department in particular, and that in itself is actually quite a, I think, nice feature to have. You know, if you're doing algorithms or if you're using probability or anything that whose applications, which means basically anything within mathematics, which has application. And if you want to provide certain service either for free or to charge clients that might drop in, I think it's a fantastic aspect. So apparently, either once a week or once every so often, Stanford lets people off the street walk in, and then a few faculty will hang around and will help try and talk to people that come in and solve their problems, or at least help them in some ways. So as it says, so this is taken from, actually I have the issue from a special issue of the Bulletin of the AMS, and the first article is a fantastic article by Percy Diaconis, who's featured here. Thank you, that's plenty. So of all people, the psychologist from the local prison walks in with pieces of such ciphers, coded messages, and asks the statisticians or mathematicians to help solve this. And okay, so this is a sample of that. And lo and behold, using fairly simple, a very standard Markov chain algorithm called the Metropolis Markov chain algorithm, they managed to break the cipher, or at least translate it into, as you could imagine, since this is a Cal State prison, it's English but with some Spanish mixed in there, and also, of course, I think Percy says in the article, prison jargon, which includes some abbreviated 4-letter words and so on. So since there are no children in the room, I hope it's not too bad. But I mean, if you just start reading, you can see that they more or less cracked the cipher from the previous page. Right? I was sitting down playing chess with Danny and Boxer. I was sitting next to the blower. Okay. And so I'll spend a few minutes talking about how they managed to do this. And Percy says in this article, he likes it because it's real, as in, it's a real problem somebody brought to them. And there's no question that the algorithm found the correct answer, because this makes sense. What they're talking about, something brewing in the prison and fighting and so on. And then the procedure works despite the implausible underlying assumptions. So of course, they made some assumptions, but what's nice is that that's fine. Even if it's somewhat of a heuristic, they managed to solve the problem. Okay, so I might go over the next one rather quickly. This is again to introduce card shuffling, and one of the nicest one-page arguments I know for a very simple card shuffle. And if I really don't make any sense, I hope at least this argument makes sense to you and you take home something. And this is again, this is it won't be due to me. I'll give appropriate credit. So this is called top to random shuffle. I will return in a couple of minutes to the problem I was talking about, breaking the cipher, okay, which was used not using top to random, but all transpositions, a different shuffle. So top to random shuffle is like your 2-year-old could do this shuffle, right? Take the top card and stick it uniformly at random in any of the positions, including placing it back on top. Okay, or all the way at the bottom, any of them. And the question is, how long does it take? How long does it take for what? Until the deck is random, meaning if I pick any card, it should be equally likely that it's any of the 52 cards or any of the n cards. Okay, that's the question. And so for most of the problems I'm going to talk about, that will be the point of interest. How long until a certain Markov chain converges to its equilibrium distribution? Most of the time, we know what the equilibrium distribution is. What we're interested in is the rate at which it approaches the equilibrium. Okay? I don't think I have a slide that formally defines mixing time anywhere, but hope it'll be clear. And so there's a simple argument that says it's a stopping time argument that says wait until the bottom card, meaning when you first started the deck, the bottom one rises to the top, and perform one more, and you can stop. Okay, how many people have seen this already? Probably lots. Okay, maybe. So why is that? Why does it work? And so there are basically 3 observations. Okay, so again, apologize to those that are familiar with this. So the first is that a card never loses ground unless it's at the top. Okay, because we are never taking something from the middle of the deck and moving it somewhere, right? Only the top one is moved. And cards might go below the existing ones, right? Okay, if you place, so you're at card I, if the top card is placed above you, it might look like you're losing ground, but you don't, because something above you is placed somewhere above you. So you stay in position, right? Okay, so that's easy to see. And so basically the bottom card slowly gets to the top at some point. And the crucial observation, the third one, is that whatever is below the original bottom is totally random. Okay, because everything that's placed is placed randomly. Okay, so that takes some reflection. And so if you buy these 3, and then now the last punchline is that when the bottom card gets to the top, of course the bottom card is not random. You know where the bottom card is. So do one more. And now that the final card is random. Okay. Yeah, of course, most of the time you're not this lucky to find such a clean, nice, beautiful answer. But again, I might go over quickly for the next calculation because that's not the point. That's a classical argument to go over. But the previous type of an answer is unsatisfying because somebody might say, well, how long is that? Tell me as a function of 52 or n, right? Or if you're a practitioner, you would be happy because for a lot of algorithms, we are able to give bounds on the mixing time or how long it takes as a function of n. Often they're pessimistic bound, but we don't have a particularly easy to verify certificate or a stopping criteria that tells you, okay, it's enough to stop the algorithm now. So in that sense, it's actually a nice feature. But if you want an answer as a function of n, it's not so nice. Okay? And the answer is basically what's usually called the coupon collector problem. And so I put some cereal boxes and stuff. And this, I don't know if this still exists or it has existed in the last 30 years. But when I was a kid, I remember my older sisters collecting, these items, and you had an album in which you systematically placed all these whatever collectibles, and when the book is complete, you sent it somewhere and you got some gift item. Right? This is a marketing gig. And so, of course, if you're collecting n items, the question is how many times, how many boxes do you have to buy so you get n distinct? Right? So hopefully everybody knows the answers to that. Yes? And the answer is? N log n. And it's a simple calculation, so let me skip over that. And the connection, so one way to see is T is the number of boxes you have to buy, and then just say, okay, what's the time to see the ith coupon, right? Ith new coupon for the first time, and then the expected time to do that is actually quite easy. Okay. So again, as I said, if there are people that are not even particularly familiar with probability, I thought I should have a couple of slides, elementary slides like that, to give them an idea of why something should be believable and to show that it's actually elementary. And then you can even estimate that the probability that n log n or n log n plus some constant time n is not sufficient is double exponentially small in the constant and so on. Okay, so the answer to this is n log n. And so there are various card shuffles. There's the top to random we just discussed, and then random transpositions, which is going to be the one relevant to the breaking the cipher problem, talks about picking two completely. So if you have a deck of cards, like here, take two uniformly at random, your your left and right hands take two and then swap the two. That's random transposition. That turns out half n log n. After that, it's close to getting random. Adjacent transpositions and cube log n, and this got cut off here. The more standard one, which I'm particularly bad at, is cut the deck in roughly half and do this riffle shuffle. It takes 3 half n log. So the reason I showed these is the story between the second and the third story has similar problems for sampling from a different combinatorial structure, and we don't have nice answers like this to any of them except for the adjacent case. Okay, so those are all open problems. While on the permutation group, there's algebra and a lot of structure, and a lot more information is known. Okay, back to shuffling towards optimality. So how did they manage to solve this? So the first thing the two undergraduates that worked with Percy managed to do was they guessed that this was probably a substitution cipher. Means there are these funny symbols, but a particular symbol is used in place of A, another symbol in place of B, and so on. Right? So in a sense, it's a problem of figuring out what is the right permutation between these funny symbols and the English alphabet. And some punctuation marks, probably. Right? Okay, so this is a technical looking slide. The point of this is to say, I think what I said here, the shuffles I talked about earlier all address the problem of sampling a uniformly random deck. Any of the permutation is equally likely, right? Any of the 52 factorial. But this problem is different because we have a particular permutation that we're interested in. So somehow you don't want to try and waste time trying to get uniform on this space. You want to guide the random walk towards the one that's the correct one. So you want to assign some fitness or plausibility or whatever function that tells you, that helps you find the correct permutation, right? So there's a standard technique, and that's the Metropolis algorithm. What this technical looking slide says is, if you have a particular distribution pi, but you would like to sample from a different distribution mu, right, then, and you have some underlying dynamics like adjacent or random transpositions, there's a simple systematic way of doing that so that it converges to the distribution that you desire rather than uniform. Okay? So I'll come back to that. So what's the fitness that one would think of? Right? How would so I have this prison cipher. What would be the symbol that I would think is the most common English letter, let's say E, right? If according to this some stat, if E, the frequency of E, this is taken from a large volume, in this case I think War and Peace apparently. So one way to do is look at if they were lucky enough to get a page or two of the prison cipher, look at which symbol is the most frequently occurring and think that maybe that's E. Yes? That's a reasonable first. Okay, so including punctuation, they came up with 28 symbols or whatever. And so the first attempt was associate these probabilities based on the frequencies of seeing these letters. And then your distribution you would like to sample from is a product using those frequencies rather than uniform. Right? Of course, it doesn't work. Or does, they ran it for a while, then they don't find anything useful. What works much better, it turns out, is adjacent frequencies. So if you see T, what's the chance the next letter is H? If you see A, what's the chance the next letter is T, and so on. So the pairwise adjacencies is how they figured out the solutions to this problem. Okay, so again, based on War and Peace or some large volume, they came up with some empirical frequencies of these P probability of seeing W2 after seeing W1 and so on. And here are the names of the two undergraduates, and ran this so-called Metropolis algorithm that tells you how to bias your walk so that you get eventually from the distribution that you would like. That gives you, so the one that has, because of this product form, so again, the I here is ranging, I plus 1 is talking about, look at the cipher text, the ith symbol in the cipher and I plus first. In the current permutation, where did f of Si go and f of Si plus 1? Okay? And it's the weight of f of Si and f of Si plus 1 I wrote as this. And then take the product. And what Metropolis does is, it goes, if it's a superior permutation, as in if it's more fit, it always goes. If it's less fit, it goes with truncated probability. Right? It doesn't reject. If you do, as we all know, strict hill climbing, you'll get stuck. Okay, so these are some probabilities they managed to come up with that just to illustrate. Q is, of course, always followed by U, T followed by H or E, or okay. And so these are the initial symbols, and the initial permutation might be this. But what we're doing is, you could do any shuffle you want. They just took the simplest transposition shuffle because in 200 runs of the algorithm, that was good enough to crack the problem. Okay? So we swap A and D. For this permutation, there's a different fitness, and with an appropriate probability, you go there or not. So as they say, after 100 step, it's a mess, but after 2,000, I guess. Any questions? Okay, my next story is the first part of the title that said something about chromosomes. And yeah, so it's chromosome mutations. I try to indicate what we are doing. Yes? Yeah, so the fitness function again is you look at the cipher and how they're mapped to the permutation, how they map to the English text, right, the alphabet in English. And for every consecutive pair of the cipher, look at what they're correspondingly mapped to. Okay, if they're mapped to T and Q, that's going to get a very low score. If they're mapped to T and H, it's going to get a large score. Okay? Take the product over all adjacencies. First and second symbol, second and third and fourth. Okay? That's it. So it encourages you to go towards the permutation. The permutation I'm talking about is between these crazy symbols or prison symbols and English alphabet. Yeah.
How long it takes to reach the endpoint depends upon what
Right. So good question. I glossed over. I talked about all these card shuffle estimates and log n for uniform distribution. I haven't said anything about how long for this one. This is a practical problem they solved and so on. But the article by Percy Diaconis talks about one or two papers they've written on a related model, a fitness function where for some parameter theta between 0 and 1, you give theta raised to distance from the identity permutation. Okay, so they made up a different problem, which is a problem on n-factorial permutations. And identity permutation has the most weight because theta is less than 1. And theta raised to distance to identity. So if distance is 0, that has the, right? So if you're away from the, so identity permutation meaning A, B, C, D, E through Z. Or if it's 52 cards, it's in some way of linearly ordering the cards. Okay, so that's the distribution. For that one, they have very precise results as a function of theta, as a complicated function of theta, and it's n log n starting from certain initial points, but there are also initial permutations that give you n squared log n and so on. So there's some literature on that. Yeah. Thank you. And again, the point of this article and lectures Percy often gives is Metropolis is a fantastic algorithm. It was invented to solve a certain hard sphere model. Ravi used to have the best result, and maybe it's now second best result on a certain Markov chain that comes from placing hard spheres in a box, let's say. And that problem is still not fully understood. So for lots of, it's easy to implement or design the Metropolis Markov chain, but figuring out how long starting from worst case starting point or average case is a tricky thing. Okay, this one, since Siddharth kindly brought some cards, this is just to illustrate. We don't have one deck now. Here I have two decks actually, but there's a parameter k, and we have k decks. Let's say k is 4. Okay. And the shuffle is called top swap. As the name says, so k is going to stay fixed. K is k. Even if there's nothing in the spot, okay, there's a placeholder. Imagine you have these tea or coffee mug coasters, and the coasters stay. And in each step, I take my two hands, I put them uniformly at random. If they fall, say, in here, and then for that one there, I do this. Okay, so I take the tops of where my, hands, tops of from the hand to all the top of the deck on each hand and swap. Okay, is it clear? And the question is, as a function of n and k, what can you say about how long does it take to get a random? What random? You could think of those k fixed decks and say n cards in total as linearly ordering them, and then there are k placeholders somewhere. If you've taken combinatorics classes, people call these stars and bars, or distributing soup cans to k or k minus 1 or k plus 1 families. In this case, because I allow one of the decks, any of the decks to be empty, it's okay to give somebody 0 soup cans. So this is a binomial coefficient, how many ways you can arrange that. And it's easy to see that after a while, this is going to get random over however many configurations. And the question is, how long? Okay, is the question clear? I hope I explained it. So one question you might have is, what happens if both hands fall in the same deck? Okay, so there are two versions. It turns out, so this, I'll say where it came from. So in the story or the problem it came from, if both hands fall in the same deck, you take that stack of cards between the two hands and reverse them. Okay, so there are two positions in the same deck, and you reverse everything in between. So my two hands fell, in these two places. So I take these cards and I reverse them, reverse the order. So it turns out it doesn't matter so much whether you include that or not. It came from an application, so okay, where on this? So the cards correspond to genes, and K, it turns out, is chromosomes. Actually, Eric Vigoda and his student at the time, Nayantara Bhatnagar, brought this problem to me and said, okay, we can prove a certain bound using coupling n square k log n square, which is n square k log n. And but we think it should be better. I said, oh, I like this problem, and then Eric said, do you want to know where it came from? I said, no, I don't need to. I'm happy to think about the card problem. So we solved it. I'll mention what the result is. And a month later, I went to Microsoft Research in Redmond, and I was excited about this. I was telling some people in the coffee lounge. The first question they asked me is, what was the motivation? Where did it come from? I said, I begged the guy not to tell me what the reality or what the background, in this case it turns out biology, was from. So of course then I had to go back and learn. So K chromosomes and inversions and translocations. So I'll show you what I mean. Inversion is basically what I said, reverse the deck of cards. Translocations is the top swap. And it's not made up, as it turned out, and one of my math bio colleagues actually supplied a couple of slides some time ago. So for these, these chromosomal mutations, people, they have names for these: deletion, duplication, inversion, insertion. So if you look at translocation, right? So you have chromosome 4, chromosome 20, and you can see it as in this picture, whatever course this was taken from, it's shown as the swapping the bottoms, but that's the same as swapping the tops, right? So this piece got attached to the red piece, and the red came to green. Okay? And inversion is here. That's the reversal. If both hands fall in the same deck, so this is the deck, they fall in the same deck, then you reverse. And this is again a slide from some class at Stanford, and this is supposedly showing, actual biological material, right? So there are these arrows pointing. You see this green and red there, and then there's a green and red. So supposedly that this is indicating that there's this kind of translocation that happened. Okay, so I'm not an expert. Any biologists in the room? Just by chance? No, so I can tell you anything I want. No. So, yeah, okay, that's where it came from. As I said, I was not particularly thrilled or excited about that. As it shows my colors. I'm in mathematics and computing, and I'm happy with that. So rather than saying any biologist, I wanted to see if anybody could make sense of this slide. Because last night I was looking at this. This is from a lecture I gave quite a while ago. And I said, what is this? And I finally figured it out. And this morning, so I got up early and I said, okay, this sounds really ridiculous. I better check whether this is true. That you can go from a cabbage to a turnip with 3 inversions, where inversion is what I just showed you, reversal of those, right, in 3. And in fact, there's a paper that appeared in JACM under the title Turning a Cabbage into Turnip and Polynomial Algorithm, Polynomial Time Algorithm for something. I'll show you the names of the people. So what this is saying is, so there's basically there are 5 blocks of this chromosome, right? And the top sequence is with the signs compared to the ordering of the bottom. So turnip has these 5 blocks, okay, call them 1, 2, 3, 4, 5. Each block is like a string of whatever material that the chromosome is made of. And when you take 5 and put a minus sign, that means you've reversed 5. So minus 5 talks about reversal of 5. So basically it's saying, apparently cabbage has 1, minus 5, 4, minus 3, 2, compared to the order in which they appear in time. So a combinatorial, purely combinatorial problem that comes up is, in how many reversals of these pieces can I get from cabbage to turnip? This turns out you can do in 3. Okay? In 3 inversions. You first flip piece 2, and then you have, and then you flip 4, and then you flip this whole. The black indicates the. Okay. So this morning, I said, okay, I'm not going to make a complete fool of myself, especially if they're biologists. And so this I got from this paper by, and I liked particularly that I managed to find an authentic sounding Kannadiga as a co-author, Sridhar Hanenhalli and Pevsner. So these are the guys that wrote a paper in JSCM with with this some actual. So the arrows indicate that this string is in this direction, and then when you reverse, you get this other. So 1, 2, 3, 4, illustrating. Yeah, so there's some legitimacy to this. And a couple of quick references. So in Genome Research 96, I found these guys introduced models of chromosomal rearrangements. They are interested in knowing chromosomal length. So this is, to the extent it makes sense to me, I think that's the distribution of the deck sizes. Right? They're not, as it turns out, Rick Durrett, who's in probability and applied probability, he formally asked the mixing question that we solve. If you do the top swap, how many shuffles does it take until you get a random? But what they're also interested in is what's the typical size of the ith deck, and so on, because that corresponds to these chromosomal lengths and so on. And again, empty decks model, these buzzwords, fission, fusion, these are also, besides translocation, these are some bio models or bio operations that's why it makes sense to keep the coaster even if the deck is empty there. Okay, so that's where it came from. And I had Pietro Capuzzo visiting me at the time, and with Pietro's help, we managed to show relaxation time, which basically means the inverse of the spectral gap, which is the 1 is the top eigenvalue of the probability transition matrix, and so the gap between the top and the second is what controls mixing time, and we showed that's order n plus k. And in terms of mixing time, as in if you measure distance to equilibrium and total variation, you lose another factor of log n, and this is a boundary. So again, I didn't put too many proofs, just because I thought after 4 Thursday, who does want to, who really wants to? But here is a 10,000 feet idea of what it took. It was not easy. So we reduced the k, if k could be 100, k could be anything. We reduced the general problem to the case of k equals to 2. So it turns out that was the hardest part. Once you have 2 decks and you can analyze, 1 deck, we understand quite well these things. So 2 deck, it turns out, was enough, because the 2 deck problem, using a weighted and unweighted deck averaging, basically every pair of 2 decks from the n deck. That's what I mean by averaging. And unweighted means, each pair is doing at the same rate. Okay, there's some Poisson clock that rings. At that rate, they do this top swap. Weighted is the version where I might have said those clocks rate based on the size of the two decks. Because ith and jth, if they have n sub I cards in the ith, n sub j and the j, if those numbers are larger, then they act faster. So we had to do this. And then there was earlier work, again inspired by these biology problems Rick Durrett brought to us. Nicoletta Concrini, Pietro Caputo, and Fabio Martinelli solved a different problem that only did reversals. Okay, and we used that and so on. And how about the two-deck itself? It turned out we had to do a couple of other comparisons. So I wrote this in sort of bluish. What I mean is, in the Markov chain analysis technology, there are techniques that let you analyze how quickly a Markov chain converges to equilibrium if you have a different Markov chain which also converges to equilibrium quickly, to the same equilibrium, but different dynamics. The comparison argument says if you can simulate a move of the chain you understand well using several steps of the chain you're trying to analyze, then there's a way to transfer bounds. Okay? As you can imagine, you need to show that no step is used too many times by too many of these pairs that you understand well. Okay, so there's technical ingredient, but the point is that if you have two different shuffles, both give you, say, a same distribution, or uniform or whatever, and you understand one well, then you can compare and get bounds on the other. So that's sort of the general high-level idea. Okay, so this sounds ridiculous at this point. If I say, what else can I show? This is like saying I have a hammer and I'm really going around for. But this has been a pet project of mine for 20-some years, and I want to quickly mention a couple of open problems here before going to the last story, and that's the kangaroo story. Okay? So all the card shuffles I talked about so far are, in some way or the other, trying to get a uniform or non-uniform permutation, right, from the n factorial objects at the end of the day. So there are lots of combinatorial objects, combinatorial structures. The top one is triangulations of a regular polygon of 5 sides. The next one is you take, imagine a circular table and you have an even number of people, right, at lunch, and they all want to shake hands, but you don't want these hands crossing and so on. So they're n pairs of handshakes, or these non-intersecting chords, or if you cut the circle and lay it down, you can also think of it as balanced sets of n pairs of parentheses, right? You have n left and n right. What's the cardinality of each of these? How many such things? How many? What's the answer? Anyway. I planted him, so he can't answer. It has to be an independent variable. So in the top one, if you have n plus 2-sided polygon, it turns out it's the nth Catalan number. In the second one, if I have 2 n points, so n chords, that's the nth Catalan number. In these peaks and valleys, n up steps and n down steps is the nth Catalan number, and so on. Okay, so there's lots of realization. And so one game you might play is each one comes with its own natural shuffle. Right? So if I were to perform that shuffle, how long does it take to get a random Catalan structure? So for example, if I'm looking at these diagrams, I might flip this valley into a peak, right? Or the peak into a valley. I might do those. Of course, if picking this flip, this peak, I can't do because I'm not supposed to go below the sea level. I'm constrained by that. Okay? And that throws a huge monkey wrench into analysis of these things. Turns out for the bottom one, actually, there's a nice tight analysis, but for none of the others. Okay? So here is the nth Catalan number. Right? It's this middle binomial coefficient times 1 over n plus 1. It's roughly 4 to the n over n to 3/2. Whatever it is. So I usually tell my students, in terms of how many there are, 2n choose n is having n left and n right parentheses. But of course, not every arrangement of left-right parentheses is a valid one, right? They have to be matching. So you cannot start with the right parenthesis, for example. So I tell a student, this is like, what's the chance that the fraction n to 3 half is, some of you might be too young for sure to know this. Back in the good old days, when politics were much less ugly, Al Gore led the whole way into the night of the 2000 election, and then they tied in the end. Or at least that was the verdict. And the chance of that happening, given the population of 8 million or whatever it was, is apparently this small. But it happened. So, but that was also to illustrate that on the space of 2n choose n, if I don't have the Catalan restriction, I know how to analyze. I can show you n log n is the bound. Okay? For some of those combinatorial. But with this, with the constraint that I should not go below the sea level, I don't know how to. So this one, with peaks and valleys, it's been analyzed rigorously up to a constant by David Wilson. That's n cubed log n. There's a famous conjecture of David Aldous that says, so what are the ones on the triangulations of a polygon? You pick a diagonal. It turns out there'll always be the same number of diagonals. Right? If you have 3, 3, 3, you pick a diagonal like this one and then flip it. Okay? We don't know. There's a lower bound that says n to 3 half, but, and that's the conjecture, we don't know that's. And you know, my first PhD student and I proved the bound of n to the 4, and that's still the best known bound. That was like in 1999 or something, 20 years ago. Okay, there are other ones which open problems. Let me move on to my last story. Any questions?
I have a question.
Yes.
In the genetic case, I'm not really a biologist per se, but how do you know any of these transpositions are like valid transpositions? For the chromosomes, maybe one of the transpositions would lead to something like the death of the cell. Like you just showed how you get from a cabbage to a turtle, but the in-between steps also should be like genetically valid. Right?
Yes, absolutely. So, yeah, very good. There was a bullet item in the references I showed. Sankoff, somebody was the first one that said they modeled it using these translocations, etc. And the second one was Day, Duret, and 4 people. So they actually introduced a fitness function to say which ones are more likely, which ones don't make any sense, and so on. Yes, we haven't, the problem Duret gave to us is like, okay, this is sort of the vanilla case, and so on. And we haven't gone back to looking at what's, I think what I said on the slide was biologically relevant. Yes, and that would be the one too. So basically, you would think biology has taken enough time that everything is mixed. But the point is they don't do at the rate that I am doing, on my piece of paper here. So if if you think you're in equilibrium after 30 million years or whatever, it might also tell you how rare it is that these mutations are happening or how frequent. And so, but this is beyond, if I say anything more, I would be blatantly lying. So let me not do that. But yeah, that's definitely valid. Okay, so unfortunately, I have way too much here I won't be able to get to. And let me skip this. Again, this is some super basic stuff to say. Factoring is hard, and also this so-called discrete log problem. I should at least tell you what the title meant. Okay, so what is discrete log? Let me skip this too. So you have a cyclic group. Okay, cyclic group basically means there's a generator G, and this is a finite group. There's a generator G, and the powers of g, g squared, g cubed, up to g to n, give you all the elements of the group. By g squared, we mean, there's some group operation multiplying g by itself, okay? And discrete log problem says, somebody gives you g raised to x mod n, they don't tell you what x is, right? Call the answer right. So they tell you the size of the group n, they generate g, and then g to n. The question is, can you figure out what x is? Okay? Everybody okay with that? Nobody knows how to do it fast. What is fast? Because this is a number theoretic problem, and I can give you all these numbers in log of the size of these, each of them, it should be polynomial in log of the largest of them. The best known is square root n, more or less. There are parallel versions. If you use J computers, maybe square root n over j, and so on. Again, I'm lying a little bit because if it's integer mod n, maybe there are tricks you can play, but if there are cyclic groups such as elliptic curve based, there's an addition over points on an elliptic curve you can define, there's a cyclic group there, and for those, nothing better than square root n. If n is usually, I should have called np for prime. So Pollard back in 1978 or so had two remarkable algorithms, remarkable heuristics, and basically the short of the story is that with the help of my postdoc Ravi Montenegro, who had also worked with Ravi Kannan and collaborators, we managed to make Pollard's very nice algorithms rigorous, as in the analysis of the algorithm. So there's heuristic that says why it should be square root of the size of the group, but then we made it rigorous. Okay. So the first one is Pollards Rho algorithm. I'm going to go over by a few more minutes. I hope it's okay. So the first time I taught this in elementary number theory, at the end of the lecture, one of the students said, "You talked about Pollard, how come you gave no credit to Rho?" And I realized I never bothered to mention that the name comes from this Greek letter shaped process that the algorithm is performing. The Rho is this. So Pollards Rho algorithm is because of it. So you start with some x0 and you apply f of x0 that gives you x1 and so on, right? The next point. Some same iterate over and over. And once you're back to something you've seen, right? Some f of xi is equal to xj that I had seen before. Then it turns out you have a good chance to crack it. Why is that? So I have to tell you what f is doing. This is one reason I wanted chalk. So if you look at the indices as g to the I mod n, right? If you look at the exponents of the elements, so this is like g to the, I should have gone from 0 to n minus 1. It doesn't matter. This is the same as 0. G to the 1, this is g squared, g cubed, and so on. Okay? So 3 means this is g cubed. So Pollard's algorithm f was you either multiply by g, multiply by h, or square the current element, each with probability 1/3. Sorry if you might not be able to see. So this function f is with a third uniformly, you either square it, you either multiply by g, or you multiply by h. If you look at what happens to the indices, if this were u, when you multiply by g, this is g to the u, so it goes to u plus 1. U plus 1, right? Multiplying by g. Squaring means u goes to 2u. That's doubling. Because this was g to the u, you squared it, right? One of the steps was squaring. So you go to g to the 2u. If you multiply by h, what happens? You still with me? Sorry? Add x, because h is g to the x, and it's x that you don't know. X is what you're trying to find. So if you look at the indices, what Pollard has done, which is very nice, is you have a walk, a random walk on a group, on a circle of length n, and it's prime here, which is relevant for this inversion. And if you were to do just 50-50 go to u plus 1 or u minus 1, it's well known that that random walk would take quadratic in the length of that would have been p squared, which is terrible, because I have a stupid algorithm that is raise g systematically, g squared, g cubed, until I find h. That takes order n. But the key, his genius was in saying, okay, I'm going to double, so the key is doubling. So now what do you expect in terms of how long it takes before I get random on the circle? Any guesses? Lot more, lot faster. I'm doubling. So if I'm trying to catch up to n by doubling each time, log, right? So turns out log, and okay, so what does this have to do with, sorry, just for a second. The point of this collision is once you've seen something that you've already seen before, in terms of the indices, it gives you a simple recurrence, simple congruence, mod n, and you can solve for it with high probability. It's not because it could be there's a small chance that what you have is degenerate. And so the question that we were faced with is, how long does it take until you see something you've seen before? So there were two approaches, one by Miller and Venkatesan, who said, well, if I'm drawing samples uniformly, that's going back to the so-called birthday paradox, right? If 365 days in a calendar, how many people should I have in a room before I see two who have the same birthday? And the answer there is? Around 23, because it's square root, right? It's called birthday paradox because pigeonhole tells us 366 with probability 1, but what this curve shows is actually far fewer. But the problem we have is we're not drawing samples uniformly from 1 through n. We have to wait until it gets to uniform by the random walk, and then you can appeal to birthday. Right? Birthday will say square root n, but then I have to wait until I get random, and hence the mixing time question. That's why I was asking you how long, and you guessed log n. It turns out the correct answer is log n log log n, at least for certain n. You can have some primes where it could be, but in the worst case, it's log n log log n. And it might look somewhat strange. Just call log n m. Then it becomes m log m. M log m is something we've seen before from as n log n. Buying cereal boxes, coupon collection. So in terms of indices, there's an argument that says it's actually until, if you've done this enough times so that if you express the indices in bits, you've touched every bit constant number of times, that can be turned into a mixing argument. So that's how we proved. And we first wrote a paper where we showed it's square root of mixing time times the birthday heuristic, square root n. So square root n, square root log log n. And this is a complicated slide, but let me skip to say, to finish my story. Yeah, I guess I don't have it. So we first showed a multiplicative dependence and showed square root n times square root log n, square root log log n. and then with Yuval Perez, we is Jonghan Kim and Ravi Montenegro and myself, we made it an additive dependence so that mixing time was not so crucial. We showed that square root n plus mixing time was sufficient under some technical conditions and so on. So we made that part rigorous. Let me conclude by saying, unfortunately, I blew my time in terms of what the kangaroo algorithm is. So Pollard was fascinated by these Greek letters. As it turns out, Rho was one. He called another algorithm lambda by the shape of the Greek letter lambda, and then changed it to kangaroo. So first of all, what is the algorithm for? Again, for crypto people, suppose some bits were revealed and you somehow figured out this x in the discrete log is between a and b. It's not in the entire circle, but it's somewhere here. Then how long does it take, or can you come up with an algorithm that still won't take any shorter than square root of the length of this arc, which would be square root of b minus a. Okay? And that was Pollard's second algorithm. At first he called it lambda, and then he called it kangaroo because I didn't even know I had this. Okay. So we wrote, my postdoc came up with this funny title saying, how long does it take to catch a wild kangaroo? And then this is a little bit of, story to share with the students that got this French newspaper, American scientists of sorts, like the French version of that, write an article about our paper. And basically, what we showed is that indeed square root b minus a is the answer. So if the entire circle is of length n, that would be square root n. But if you know it's somewhere in between a and b, in an interval between a and b, it's square root b minus a is still the hardness. And the kangaroo name comes and because Pollard's solution was you don't know g to the x, but make it take increments, certain bounces that are powers of 2, and then but you start a known g to the y and do the same bounces. So we call that one tame kangaroo. And once the two collide, which happens with some probability after 2 times square root b minus a step, it turns out you can crack what the discrete log is. So it's those jumps that made him call this lambda-shaped algorithm kangaroo. And I'm awfully sorry, I'm way over time, so let me stop there. Yeah. Yeah.
Perhaps it's
here is a theorem.
this is a class of generic what they call the baby step, giant step process, which will apply in any group. In the sense, take small jumps and then at some point on take that order, that element wherever it lands, and then take double the index value or something like that.
Right. So I never told you what the kangaroo algorithm was in terms of what the jumps were. So thank you for giving me another minute. So you have a set of jumps, and Pollard took the jumps to be, meaning if I have x, what is x plus, what's the jump size? Jumps to be 2 to the 0, 2 to the 1, 2 squared, powers of 2, as an example. And how many jumps? It turns out the average jump size is what's relevant, and the average jump size should be square root b minus a. You have an interval of length a, from a to b, of length b minus a. Okay? So the average is like square root of that. And what we show is if you start randomly, uniformly randomly from anywhere on the interval, it takes 2 times square root b minus a. If you start at one of the two ends, it's 3 times. So the constant is quite small. But we also proved a conjecture of Pollard that said you can have all kinds of jumps, but powers of 2 is actually the most efficient, and we proved that. Now, with the jumps, what do? What you do is you give both g to the x, where you don't know x. This is the wild kangaroo. But then I choose some x0 I know, and g to the x0. So I have my jump sizes powers of 2. I pick uniformly at random one of them, or with some distribution, so that the average jump length is square root b minus a. Both the kangaroos use the same jump size. That's the algorithm. Because that way then you maintain an invariant that tells you there's a set of traps you put. Okay? You can wait until the end, right? Because if they fall, because they're using the same jump sizes, if they ever meet, then they'll continue to stay together. And so your trap could be at the end, but in Pollard's algorithm, he places a few traps so that there's a chance of stopping before. That's kind of the general idea. There's a nice card trick you can Google. It's called Kruskal card count. It's a very nice card trick you can do with anybody and make them think that you figured out what card they guessed. Right? It's really cool. And this kangaroo algorithm is based on that. Thank you.
Here we have advisor of Prasad. I will request our Venimadan to present the memento to Prasad on the
Yes, I did my master's with Venimadan. I totally forgot to mention that. So thank you. And all the number theory stuff I got into is thanks to him. Thank you again.
Thank you, Prasad, for a wonderful talk. And also, I'd like to thank Professor Venimadhavan and Professor Ravikannan for being our chief guest, and also Professor Narahari and Professor Shalav for arrangement, and as well as the administrative staff, volunteers, and all CSA community. And there is a high tea just outside. I would like to invite all of you there. Thank you.